Today I'm going to show you a magic trick. With me here is a coil of wire connected to a 50 Hz AC power source. The voltage across the coil is about 6.12 volt and the current is about 2.1 ampere. Without touching the power setting, I'm going to change the applied current of the coil. Ta-da! The current drops significantly when we put a screwdriver into it. You may wonder how this works. Let me give you two hints. First, it does not work if we put anything inside. For example, if I put my finger inside, it doesn't work. It will also not work if I put an aluminum rod into it. But it works with a screwdriver. Second, this is actually a regular screwdriver that is not magnetic. But if we put it inside the coil, we find out that it will become magnetic. So we know that the magnetic field plays a role into this. To further understand the reason, we will have to first understand something called inductance.
When a direct current flows through a wire, it will experience a resistance and also generate a magnetic field around the wire following the curl right-hand rule. Ohm's law tells us that for a given voltage, the higher the resistance, the lower the current. What if we now have an alternating current instead? It will generate a time-varying magnetic field. This changing magnetic field will create an opposing electromotive force along the wire, which depends on the rate of change of current. And the proportionality constant L is known as the inductance. We can think of the inductance as an additional resistance to current flow, also known as reactance. And the reactance is equal to the frequency of the AC source times the inductance of the electric circuit. So the larger the inductance, the more reactance the wire will experience, and the smaller is the current. You may wonder what determines the inductance. The inductance depends on the geometry of the circuit and how easy the surrounding materials can be magnetized, also known as magnetic permeability. When we coil the wires into loops, we form what is called an inductor. There is larger resistance to current change, and the inductance is larger. The inductance of a coil of wire can be expressed in this equation, where N is the number of loops of a coil, A is the cross-section area of the loop, L is the length of the coil, and mu is the magnetic permeability of the medium. Let us first explore the effect of the number of loops of the coil on its inductance.
We can measure the resistance and inductance of the coil of wire with an LCR meter. Here we have a coil of wire with 400 loops, and the resistance is 2.41 ohm, and the inductance is about 3 millihenry. On the left here is another coil of wire with the same dimensions, but with 1,600 loops. The resistance of this new coil of wire is 40.3 ohm. That is because the wires are thinner, so the resistance is higher. The inductance for this coil of wire is about 47.7 millihenry. Because the number of loops is now 4 times the previous one, the inductance is about 16 times higher.
We note that the inductance also depends on mu, which is the magnetic permeability of the surrounding material. So it is possible to change the surrounding medium of the coil to change its inductance. Going back to our magic trick at the beginning with the 3 millihenry coil. Here the medium around it is air. Inductance is low because air can hardly be magnetized. When we put a screwdriver into it, inductance increases because the screwdriver is made of an iron-based material which can be easily magnetized, so mu is larger. As a result, the reactance of the coil is increased, and that is why the applied current is reduced. If we use a thicker iron bar, the effect on the inductance is more significant. Here, the inductance is increased to about 16 millihenry. Since the magnetic field is also created outside the loop, inductance of the coil can be further increased by replacing the short iron bar with a U-shaped bar, like this. For this U-shaped bar, there is still an air gap at the end of it. Closing this air gap with an iron bar can further increase the inductance to about 80 mH, which is much higher than the 3 mH with an air core. I hope you get a better understanding of inductors in this video and also the factors affecting inductance. Inductors are very common in our daily life, from transformers in power stations to wireless charging and induction cookers. Stay tuned for our next videos to discuss how they work. Bye bye.